Okay, I think I finally got this written down right. And excuse the mistakes, but I really don't mind making them because I've asked you to work them out for yourself and given you the opportunity to beat me on these. And mathematics is all about beating the other guy. Well, some people are pretty competitive about it, so feel free to be competitive. It's about understanding it. It's about seeing just how neat all this is, and it really is very neat. When it's all pulled together, it's really kind of spectacular. And I'll try to indicate why that is as we go on. Okay, right now we're just working through some mundane details, but we understand that we're doing average rates of change, except now that when we take the limit of our average rate, we get what we call an instantaneous rate. It now isn't an average rate over a finite change in x. It's what we get when we change that finite, or let that finite change approach zero, and our average rate approaches what we call an instantaneous rate. Now we'll understand that a little better when we represent it on graphs, which is what we're going to do after we finish working this one out. Okay, so let's see. First of all, if delta x approaches zero, then the cosine of delta x, the sine of delta x approaches zero, and that's obvious. As I say, it's getting a little bit late in the day. I've been at this a while. Okay, your circular definition of the sine function, if you have, or sine or cosine functions. If you have a small delta x being this angle, and that angle is in radians, if you have a small delta x, then the sine is what? The sine is just this coordinate. The cosine is this coordinate. And of course, we're talking about the unit circle definition, and I assume you're completely aware of how to use the unit circle and how it represents sines and cosines. If you're not, you need to be. Okay? So, the sine is this coordinate, the cosine is this coordinate. Clearly, as the angle delta x approaches zero, what happens to the value of the sine? Well, the closer this gets to zero, the closer this gets to zero. Now, it turns out also, and it's kind of important to understand this, because if this angle is in radians and this is a unit circle, then this arc here is equal to the delta x, and the arc is equal to, almost equal to the opposite leg, I'm looking for a word, didn't want to say side, opposite leg of the triangle from the angle, and that is used to show that the sine of delta x for small angles is very close to delta x. Okay? So, we use that along with the idea that the sine of delta x does approach zero, but the sine of delta x over delta x approaches 1. Now, I'm not going to do the details of that. Maybe I'll follow up with a subsequent video on a bigger picture, and I'll indicate a little bit more about why that is. It's something I kind of assume you've seen at this point. So right now, at least accept this, and accept that the cosine as delta x approaches zero, this approaches 1, and the cosine of delta x, and this is pretty obvious, approaches 1. Okay? Because obviously, on a unit circle, as this angle gets smaller and smaller, you approach the point 0, 1 here. Okay. So, using that, we can rewrite this as cosine of x times the sine, well, let me write it a little better notation, sine of delta x over delta x plus what? Excuse me. Plus this, okay, all this over delta x. Now, at the limit as x goes to 0, or delta x goes to 0, of all this, you know, this thing plus this thing, I'm not going to write out, is what? It's cosine of x times 1. So we got a cosine of x times the limiting value, sine of delta x over delta x, which I'm asking you to at least believe is 1. And then what we have is sine of x multiplied by 1 minus the limit as delta x approaches 0 of the cosine of delta x minus 1 over delta x. So we've got a cosine of x, and we got a sine of x times this. Okay? Now the question becomes, what happens to cosine of delta x minus 1 divided by delta x? And this work gets kind of difficult to see, and I'm probably going to need to follow up with a bigger picture. It turns out that the cosine of, well, if you look at this picture, cosine of x minus 1 is just the difference between this projection here and 1, okay, because here's 1. So here's your cosine of x minus 1. It's really small. Whereas delta x, I mentioned before that the arc delta x is right here. You see that this arc is a lot bigger than this little minuscule sliver here. I need to write it with a bigger picture. But it turns out then that since the arc delta x is much bigger than this, as delta x approaches 0, as this angle approaches 0, as this sliver gets smaller and smaller, this one gets smaller very fast, much faster than this one does, so that this representing that little sliver, this representing the arc, gives you a limit of 0. Okay? And it can't equal 0. I mean, it has to equal 0. We don't have a 1 minus there. That was a mess up on my part. I was factoring. So we'll continue with this one. Just want to make sure I factored right, and I'm sure I did. So we have to see how that works out.